All right, let's jump right in. We're going to talk about the invisible world of forces. You know, they're the hidden hands that are literally keeping planets in orbit, sticking magnets to your fridge, and even powering the very device you're using right now. So what's the connection between all these things? Well, that's what we're here to figure out.
So, what do a planet, a magnet, and a soccer ball all have in common? I know, it sounds like the start of a bad joke, right? But the answer is actually incredibly simple. They're all governed by forces. These are the basic pushes and pulls that control how pretty much everything in the universe interacts with everything else. So the big question is, how does it all really work?
Okay, so first up, a world of pushes and pulls. We've got to start with the absolute basics to get a handle on this, right? We're talking about the simple forces we feel every single day.
So what is a force? At its core, it's just a push, a pull, or a twist acting on something. Seriously, that's it. And when scientists want to measure it, they use a unit called the Newton, or N for short. And yeah, it's named after that Newton, Sir Isaac. And trust me, we'll be hearing a lot more from him soon.
And what can these forces actually do? Well, they have some pretty powerful effects. Think about it. When you push a shopping cart, you're using force to make it go faster or slower. When a goalkeeper punches a soccer ball away, they're using force to completely change its direction. Heck, even just squeezing a loaf of bread to see if it's fresh, that's you using force to change its shape. These things are happening all the time, all around us.
All right, next section, forces, seen and unseen. It turns out we can sort all these forces into two big categories. And you know what? This difference is absolutely crucial for understanding how the universe really works.
Okay, so on one side you've got contact forces. These are the easy ones, the ones that make perfect sense. You have to literally touch something to make it move. Think about pushing a trolley or the friction from your sneakers on the pavement. But then, you've got the other side, the non-contact forces. These are the weird ones. They act over a distance, through empty space. It's like a kind of invisible hand. Gravity, for instance, is a non-contact force, and it's the only thing keeping you from floating out of your chair right now.
And that brings us to the real heavy hitters, gravity and magnetism. We're talking about the universe's invisible architects here. These two forces shape absolutely everything, from the way whole galaxies are formed down to which way a tiny compass needle points.
And look, we're back to Newton. His big idea about gravity was just brilliant. He figured out it's basically a cosmic tug-of-war that boils down to two simple things. How much stuff an object is made of, that's its mass, and how far apart the objects are. The more massive something is, the stronger its gravitational pull. But, and this is key, the farther away you get, the weaker that pull becomes.
So just how strong is this pull we're talking about? Take a look at this number. That is the gravitational force between our sun and the Earth, measured in newtons. That's a 36 with 21 zeros after it. I mean, that's just a mind-bendingly huge number. And that incredible force is what keeps our little planet swinging around the sun, year in and year out.
Now, what about magnetism? Well, it works in a very similar way. It's what we call a field force. So, just like a huge object like the Earth creates a gravitational field, a simple magnet creates a magnetic field. Think of it like an invisible bubble of influence that surrounds it, ready to attract or repel other objects that come near.
And the rules for how they interact? They're so simple. Every magnet has two ends, a north pole and a south pole. If you bring two different poles close together, say a north and a south, boom, they snap together, they attract. But if you try to push two of the same poles together, like two norths, you can actually feel them push back. They repel. It's that simple rule you learned as a kid, opposites attract and likes repel.
Okay, time to talk about harnessing this power. We're moving from just understanding these forces to actually controlling them. This is where humanity pulled off its greatest trick. We took what we learned about these field forces and used it to build the electric circuits that run our entire world.
So what exactly is an electric circuit? Well, at its most basic level, it's just a closed loop. Think of it like a racetrack for a flow of electrons, which is what we call an electric current. As long as that track is complete, the electrons can keep flowing. But the second you break that loop, which is exactly what you do when you flip a light switch, the flow stops. It's that simple.
But just like in a real race, not all tracks are created equal. Some have more, let's call it electrical friction or resistance. This makes it harder for the current to flow. For example, a really long wire has more resistance than a short one. A super thin wire has more than a thick one. Even temperature makes a difference. A hotter wire actually resists more. And of course, the material itself is huge. That's why we use copper for wiring. It's like a wide-open superhighway for electrons, with very low resistance.
And the way you design that racetrack is incredibly important. You've got two main options. First, the series circuit. Here, everything is lined up in a single file. The problem, if one thing breaks, like one light bulb burns out, the whole circuit is broken, and everything goes dark. Then you have the parallel circuit. This is much smarter. The current splits offering multiple paths. So if one bulb goes out, no big deal. The others stay on. And this right here is why your house is wired in parallel. It's so that plugging in your phone doesn't suddenly turn off the refrigerator.
All right, let's zoom out. We're going from a single little circuit to powering your world. Let's look at the big picture, the national grid. How do we make enough electricity to power entire countries?
Well, in a classic coal power station, it's really a big chain reaction of energy conversion. Step 1. You burn coal to get incredible heat. Step 2. You use that heat to boil water and create super high-pressure steam. Step 3. That powerful steam is used to spin a giant fan, called a turbine. And finally, Step 4. That spinning turbine is connected to a generator. And this is where the magic happens. The generator uses magnetism to turn that spinning motion into electricity. So you go from heat to steam to motion to electricity.
So, what does all this mean for your wallet? Let's bring it home. Firing up your TV for an hour? Yeah, that's pretty cheap. But look what happens when you use something that really draws power, like a microwave, or especially an electric heater. The cost per hour skyrockets. That space heater, for just 1 hour, can cost you more than 7 times what your TV does. It's a huge difference.
But here's something that might blow your mind. Before that electricity even makes it to your house, a huge chunk of it is just gone. It's lost. About 15% of all the energy that's generated at the power plant gets wasted as heat in the power lines and all the equipment along the way. That's energy that's paid for, but never actually gets to do any work in our homes.
And so that really leaves us with one big question, doesn't it? We've managed to go from understanding the simple pushes and pulls of the universe to building this incredible, global, electrified world we live in. But now that we know about things like resistance and all that wasted energy, it makes you wonder. The real challenge for us, for tomorrow, is how do we take this knowledge and do it better? How do we harness these amazing forces more efficiently and more intelligently? That's the question we need to answer.